The third test for maximums and minimums is called the second derivative test. So far we've talked about the first derivative test where you show a sign change on the first derivative, and that helps you justify whether you have a maximum or a minimum. And the candidates test, which says, well, the only places where I could possibly have minimums and maximums are endpoints and critical points, so I'm just going to compare my y coordinates at those points. And the second derivative test, which is another way of justifying maximums and minimums. In order to use the second derivative test, you need two things. You need a first derivative that's equal to 0, so your critical point can't be the kind of critical point where your first derivative is undefined. If you have that kind of critical point, then your second derivative also won't be defined, so the second derivative test won't work. And then you also need your second derivative to not be 0. If your second derivative is 0, you can't use the second derivative test. But if your second derivative is negative, then that means that you have a horizontal tangent line and your function is concave down like a frown. And so that would help you justify that there is a maximum value at x equals c. Same thing for minimum, except that's a concave up. And so you would have a minimum at that critical point. So reasons to use this test, why don't you just always use the other two tests? And usually you can get away with just the other two tests, but this one is, sometimes the justification is just easier to write. Sometimes you're not going to have access to f or f prime, and you'll be given f double prime instead of f or f prime, and then you can't use either of the first two tests. And for implicit differentiation, with both x and y variables changing, it's really impossible to talk about a sign change of f prime at an x coordinate. So you have to rely on the concavity of your curve at that point. All right, so we'll do this first example. We'll use the second derivative test to find where the maximum and minimum values occur. So we're going to start by taking a derivative. I hope you're getting by now that this chapter, if you don't know what to do, at least take a derivative so you can get some credit for having the correct derivative. And then this is a quadratic, so it's never going to be undefined. That's good because we can't use second derivative test if it's undefined, so we're going to factor here. And then we have critical points at x equals 4 and x equals 2, and both of those critical points are the kinds where we have horizontal tangents. So we are set up really well to use the second derivative test, so I'm going to go ahead and do that. So the second derivative at 4 is 24 minus 18, or 6. And the second derivative at 2 is 12 minus 18, or negative 6. So this is really the joy of the second derivative test. We know that y of 4 equals 0, and we know that y prime of 4 equals 0, and we know that y double prime of 4 is greater than 0. And it's important to show that what number it is if you can. So y of 4 is a minimum. That's just really easy to write. And then if we wanted to do the other point, we would say y prime of 2 equals 0. Y double prime of 2 is less than 0. So y of 2 is a maximum. If you need to draw out, greater than 0 means we have concave, greater than 0 means we have concave up like a cup. And we have a horizontal tangent line, so there's a minimum at that point. Second derivative less than 0 means concave down like a frown, horizontal tangent line, so we would have to have a maximum at that point. We are given, for the second example, we're given an implicitly defined relation, and we're asked about a critical point on that relation. So our first step is to take a derivative. We'll have to do it implicitly. So we have 2y times dy dx minus 10x plus 2 dy dx equals 0. I'm going to move the 10x over, so I have 2y plus 2 dy dx equals 10x, and then I'll divide. Dy dx is equal to 10x over 2 times y plus 1, and I can factor a 2 out of that, so I have 5x over y plus 1. And I can see that I have a horizontal tangent line at x equals 0, so I can use the second derivative test, which is good because I can't really use the first derivative test. It's really hard to talk about a sign change when both x and y are changing on your derivative. It's hard to talk about a sign change. So we're going to take the second derivative, and we'll do low d high minus high d low all over the square of what's below. And I would not waste your time with any algebra. I would jump right to plugging in numbers. We know that x equals 0, we know that y equals -4, and we even know that the derivative is equal to 0 because we've already examined that a little bit. So we're going to go ahead and plug those numbers in. So -4 plus 1, and this, whatever that is, would be 0 because dy dx is 0, and then over -3 squared. So we have -15/9 or -5/3. And we can conclude that this is a concave down at x equals 0. So we know that our curve goes like this, has a horizontal tangent line. So 0, -4 is a maximum because dy dx is equal to 0, and the second derivative is less than 0. For this last example, we're given the second derivative. We're not given f. We're not given f prime, but we are told that the first derivative is equal to 0 at 1. So we are going to evaluate the second derivative at 1, and we get -2 times -4 times 3, which would be +18. Nope, +24. And that tells us we have a concave up like a cup. So we have a minimum at x equals 1 because and that justification just takes a lot less words than the justification for the first derivative test. And we also don't have the first derivative, so we don't really have a choice here. All right, that is the second derivative test for extreme values. You need a horizontal tangent line, and you need a second derivative that is not equal to 0.